So, at first, thanks to all of you, because you are here on the last day of the conference at this 8:30 time. My name is Ferran Teneri. I'm from the Montfort University, and as a second affiliation from the University of Jyväskylä in Finland. And the title of this talk is going to be Understanding Differential Evolution. I have been asked here to speak for roughly 1 hour about differential evolution. I was thinking exactly what to do. And I was thinking how to find a compromise in order not to bore you too much. And a compromise was between speaking about too much basic stuff and going too much into the details. Then I thought that a possibility is to discuss about the algorithm and about the algorithmic philosophy. Let us see if you are going to like it. So this, yeah. So what to expect from this keynote? I'm going, of course, to follow the instructions and talk about differential evolution. And I'm going to justify why D is so popular. And this means to try to find an explanation about why does D work. Then I will still keep on asking to myself, to you, why is D so popular? Which means to ask to myself and to you, why does D doesn't work? And then let's say we have this final question is, what is the community doing to enhance upon D performance? And then what could happen in the future? So a bit of a historical notes. Differential evolution was proposed by Ryan Storr and Kenneth Price in the 90s. And originally it was a procedure to solve the fitting of Chebyshev polynomial. The novel point when differential evolution was used was to make use of difference vectors, so to perturb the populations, to perturb the individuals by means of these difference vectors. What are the general features of a differential evolution algorithm? At first, we can say that it is a population-based. So population-based algorithm means that processes a multiple set of solutions. Secondly, it's a stochastic algorithm. And then the search logic is based on difference vectors. And this means, because we have to compute the differences, that the D is kind of structured for continuous spaces. So it is an optimization algorithm that is stochastic, that is population-based, and that is mostly used to address continuous optimization problems. The general D scheme is composed of initialization, which means that a set of points are sampled. Then there is a generation cycle, as in most of the evolutionary algorithms, where mutation and crossovers occur. And then there is the survivor selection, which occurs according to this technique, one-to-one spawning. I will go to the details in a while. So initialization, at first, let me say that without a loss of generality, we are referring to the minimization problem of a certain function f of x within a decision space D. At the beginning of the process, simply a set of points, or I'm going to use sometimes the word point, sometimes the word vector, sometimes the word candidate solutions, are sampled within the decision space D. When all the solutions are being generated at the beginning, randomly, what happens? It happens that for each of these solutions, let's say, which means a for cycle, for I, which goes from 1 till n, or from 0 till n, and till n minus 1 if you are a C programmer, it happens that the solution is taken into account and a mutant solution is generated. There is in literature plenty of mutation schemes. These are just some examples that have been reported. So if we consider the classical one, the so-called D-rand one, it means that 3 solutions, XR, XS, and XT, are sampled randomly from the population, and they are combined by means of that formula, where F is a constant number called scale factor. And this generates the mutant vector, or as I like to call it, the provisional offspring. So at the moment, I'm not doing anything with xi that I'm taking into account, because I'm going to use xi in the following step, in the crossover. And there are two popular crossovers at least, or two, let's say, traditionally popular crossover. The first one is called binomial crossover. And it basically means that some genes are swapped from the mutant to the offspring solution. So, or better, that the offspring solution is a crossover between the mutant and the parent, where the genes belonging to the mutant are selected by means of that criteria. If a certain random number is smaller than a certain threshold, then the gene is copied. So this means that they become scattered, so that a scattered sequence of genes is copied into the offspring. Or we can have the exponential crossover, where instead of having an if, you have a while, and this means that I'm going to copy a sequence of genes from the mutant to the offspring. So that means that the offspring is basically made up like a parent, except for a section of it, which is a mutant. I think you are pretty much familiar with it. And then there is the survivor selection. This is a little bit more interesting. We will go back about this in a while. So when all offspring population is generated, for each individual, the fitness value of each offspring solution is computed. And if the fitness, so we are referring to minimization, is less or equal, if the fitness of the offspring is less or equal than the fitness of the parent, then there is a replacement. And this technique is called one-to-one spawning. This graph, it's actually something that I've done myself from Google Scholar, nothing special. I just tried to see how many papers about differential evolution are being published over the years. And you can see that there is this kind of monotonic trend. And now, I mean, in 2012, there were nearly 7,000 publications about this topic. And basically, the point of this keynote is to give an explanation to this graph and to say, why is this happening? And at first, we have to say that the differential evolution is an extremely simple scheme. And it can be done even by a student very easily. And in order to code it, it requires just a few lines. And it can be easily applied in several cases. And it can be easily applied because let's say it's versatile. It can be easily applied in several fields, and it has only three parameters to be tuned. And so it means that without much effort, I can just adjust my algorithm to solve every kind of problem, more or less. As a further important step, DE does not really, I mean, the DE implementation does not really require a brilliant mind, meaning that it requires a very little knowledge in mathematics. So with a very modest knowledge of mathematics, I'm able to implement a differential evolution, understand more or less what is ongoing, maybe not in depth, but enough for solving an application, tuning it, and adjusting all the parameters, and customize my algorithm in order to address a given problem. What is the classical DE working principle? So what is considered to be the working principle in differential evolution? So we can see the search as a progressive randomized movement, and the search is moved towards the optimum. So you can think that we have this set of points, and this set of points are evolving, or this set of points are sampling within the decision space. And of course, due to the survivor selection, better and better points are selected, and which means that we have better and better populations, and eventually the points are moving towards the optimum. A not very popular explanation, but I think a very interesting explanation, is the so-called Feoktisov explanation. This comes from 2006, from a book. And it's pretty interesting, if I can make a side comment, how this explanation is disregarded in most of the papers about differential evolution. what does he simply says? He says something quite trivial, to be honest, but still quite interesting. It says that at the beginning of the optimization problem, the points are sampled within decision space, and therefore they are more or less scattered within decision space. And this means that the search radius, which for the mutation formula depends on the point, is kind of big. So I have a large search radius, and so at the beginning the algorithm is very explorative. And this is what I want, in principle, to do at the beginning of an optimization problem. Then, if the algorithm is working, the population of solution tends to focus towards the interesting areas. And what happens then? That since the search radius depends on the distribution of the solution within the decision space, the search radius becomes smaller and smaller. And in other words, this means that the algorithm is becoming more exploitative. And it is exploiting the available solution towards the optimum and to end the game. So, Kryptisov was saying that a D scheme is characterized by an implicit adaptation. So even if I have a non-adaptive differential evolution, even if I have a very standard differential evolution with a constant scale factor, still, due to the dynamic of the population, the algorithm contains an implicit adaptation. And, well, okay, this is what I've told you already, so that the population shrinks, and therefore from an explorative algorithm, it is supposed to become more and more exploitative. But then, let's say a bit of a provocative question. Is DE such a perfect system? I've shown you earlier the graph about D papers. Many of these D papers are on applications, but probably more than half of them, or well, it's actually about half of them, are papers that propose enhanced versions of differential evolution, modified versions of differential evolution. And then why is this happening? Well, the answer is pretty trivial. And it is that it's very easy to improve upon the performance. And or in a more politically correct way, D has a wide margin of improvement. And it happens that even if these variations are minimal, so I just modify a little thing here and there, then I obtain a much, much better performance. Now we will try to understand why this is happening. And so what are people doing in order to improve upon the performance? Maybe consciously or unconsciously or randomly or for any kind of reason. And therefore what we as a D community can do in order to make the correct variation, the correct modification of the D scheme in order to improve upon it. So, at first, let us start criticizing the D scheme. So why does it have such a wide margin of improvement? Before getting into the details of D, I would like to make, let's say, a little discussion about notation and about what is an optimization algorithm. At the end of the day, every optimization algorithm is an iterative process, and all the optimization algorithms have the same structure. So there is nothing special behind an optimization algorithm, and each optimization algorithm is composed of one solution or a structure of solutions, which can be a set of solutions, that we are going to call elite. And then these solutions are perturbed in some way. So you can think about the GA, or you can think about an evolution strategy, it doesn't matter, but, or you can think even about any kind of gradient or exact method. Still, it means still every algorithm has some solutions, and then the solutions get perturbed. And so trial solutions are generated. Then there is some kind of fitness-based comparison in order to elect or to select the new elite. Said this, within a D scheme, the elite is the population of candidate solution. And the trial structure is nothing else but the offspring. So in this case, it's really straightforward. And so for fixed values, let's say, so we have the elite, that is the population, the trial is the offspring population, and then by means of the survivor selection, it is selected, or it is elected, the new elite. Very easy. So for fixed values of F and CR, so of scale factor and crossover rate, and population, and for a given population, we can think that a differential evolution has an implicit pool of movements. That means that, well, you can think about the mutation strategies, the simplest, the round one. And so you can think that the pool of possible points that can be reached from a differential evolution at every single step is already contained within the information of scale factor, of crossover rate, and let's say population scattering or population distribution within the domain. So we can think about that we have so this pool of points that can be reached, or in other words, we can think that we have a certain set of search moves within the framework. So we can think that at every step, D is carrying a certain amount of search moves. The first drawback in a D scheme is that this amount of search moves is limited. This is something I was analyzing it myself, and what I've been noticing is that there is at the end the points that can be reached are not that many. So in a very trivial way, we can say that in order to enhance a D, the right thing to do is simply to add some additional search moves. And actually, pretty much all the literature, or most of the literature that is proposing enhanced D versions, is simply including new search moves within the D search, nothing else. And it is somehow compensating this deficit by enlarging the pool of search moves. Now we have, let's say, these questions. So, okay, yeah, I have to improve or to enlarge the pool of search moves. How can I do it? There are two popular ways of doing it, or let's say according to a classification that I like to make. One is by explicitly, or actually even implicitly, including some additional alternative search operators. So, and I like to call this mimetic approaches. And the second way is by integrating the framework with a certain degree of randomization. So randomization is also something that allows allows an enlargement of the pool of search moves. Let us go through some popular variations or enhanced D versions, and let us see how they behave, what has been done in the literature, and how they can fit in one or in another category. This is, let's say, an algorithm from 2008, and it proposes an adaptive crossover local search. In this case, it's pretty straightforward what is happening, and without getting into the details, I'm just putting the pseudocode over there. What you have to think is that the crossover does not happen exactly like I showed you earlier, but there is this modified version that includes some, basically a simplex, in order to select the best offspring. And this is clearly a mimetic approach, and this is clearly an approach that integrates, that injects new search moves within the framework. A second one is this one, which was, this has been done by me and my colleague in Finland. And still, it is a local search, but it is performed on the scale factor. So it's nothing else but a linear search. And it is yet again a way to control the generation of the offspring. So, and it is, it can be seen at least as an additional search move within a differential evolution framework. So you have to think that. So in this case, you have a differential evolution that works as I explained earlier, but the scale factor is kind of tuned by means of a local search every time, or actually every now and then by means of some probabilistic criterion, in order to select the proper one that guarantees a promising offspring. This is another, well, let's say popular DE variation, and it is called opposition-based learning. And in this case, what the authors were doing was simply to sample some extra solutions within the indecision space by using a central symmetry. So they are testing some extra points here and there. And this is yet again an operation that allows extra search moves. And it has some benefits, and it can be seen like a shallow local search, because I am selecting between two by means of a deterministic criterion. Or this is another popular approach. There are several papers about this. I'm citing two. One is the pretty famous algorithm called the SAVE by Professor Shubentan, and this other one is called ensemble of differential evolution mutations, well, ensemble parameters and mutation strategies. And in this case, what happens that instead of using only one mutation strategy, multiple mutation strategies are used, and they are coordinated in some way. So simply, I'm not using only one way of generating the offspring, but I have several ways and coordinating them in some way, and I am enlarging the pool of search moves. Now, this was pretty much straightforward. I hope I didn't bore you too much. Now let's say, look at the things a bit in a different way. And let us look at the second category, and it is this randomization. So if I have a certain randomization of the control parameters, what do I have? I have more points that I can reach. So if, for example, f is randomized in some way, so this famous jitter or jitter, it means that potentially I can reach many more points. And this means that the pool of search moves is really big. So I could think that if I want a very big pool of search moves, the only thing that what I can do is simply to have a randomized scale factor and a purely randomized scale factor. But do I really want that? Actually, what happens is that if I have too much randomized parameters, I have maybe a too large pool of search moves. And unfortunately, most of these search moves are unnecessary, and I don't want them. A good compromise has been given in 2006 by Johannes Brest and about this so-called JDE, where he's proposing basically a controlled randomization of the parameters. Without getting too much into the details, you can just look at these formulas, and basically those formulas mean that the parameters are updated every now and then, not always, and they are more perturbed rather than fully reupdated. Well, the crossover rate is reupdated, but the scale factor is not. It's just perturbed, and it is slightly modified. And this simple modification of a differential evolution scheme was very promising. It's still very promising, even with respect to modern algorithms. And at the end, you see that the variation that has been performed is pretty limited. And this means somehow that what we want in order to have a fully functional differential evolution is a certain degree of randomization. We do not want it too deterministic, we do not want it too randomized. Pretty much by means of the same philosophy, the randomization can be achieved by sampling the parameters not from a uniform distribution, but from a non-uniform distribution. And well, this is also pretty straightforward. If you think about the mutation formula, and you think about a randomized scale factor, if the scale factor can vary, for example, between 0 and 1 by means of a uniform distribution, and I try to sample 100 times the scale factor, I'm most likely going to get one for 100 different scale factors that are pretty much so uniformly distributed, so that they are the different one from another. But if I use, for example, a Cauchy distribution, that, or well, let's say, if I use a Gaussian distribution, what happens is that they are going to be not that diverse. And this is yet again, apparently, something that works within the differential evolution scheme. Well, just a little note. What is used in several model papers, actually without any theoretical reasoning behind that, but is the Cauchy distribution. But basically, unfortunately, nobody has a theoretical explanation of why a Cauchy distribution appears to offer some benefits. Nonetheless, what I would like to remark is that it's due that this choice is probably due to the shape of the Cauchy distribution. That so usually it is because it's larger. That's what, let's say, people say. And it is if I use a Gaussian distribution, I tend to have a much sharper, let's say, shape in the distribution. And apparently it's a bit harder to adjust it simply by tuning the standard deviation. But anyway, this is what this may be a too technical comment for today. Another way of injecting some randomization within the scheme is instead of sampling the scale factor or crossover rate, I can sample the individual itself. So this is the compact differential evolution. And it means that, so in this case I have not a population, but I have a statistical representation of the population. And the individuals are sampled from it. So the randomization is not in the scale factor, but it is in the individual itself. Or, in this other case, that is still based on a compact differential evolution, I have this disturbed exploitation compact differential evolution. And in here I have the sampling from basically from two distributions. So this means that actually I would like, in this regard, to show you the video. I hope this is going to work. Yeah. So this is pretty much our compact figure. So what I mean is that individuals are sampled from a distribution which at the beginning is pretty much like uniform, and then it goes converging in some points. But in order to avoid a premature convergence and so a diversity loss, this other scheme modifies the previous one by basically allowing a restart. And the restart means to include a second kind of randomization. That means that every now and then this sharp distribution becomes wide again. And oh, what happened now? Sorry. Fine. So it becomes wide again, and I'm going. So that means that my search radius becomes smaller and smaller, and then at some point it is enlarged again. And this apparently had great benefits also on the performance of a compact D. But okay, now I've been speaking for about half an hour about these search moves of differential evolution, and I covered some of the literature on it. And I try to explain how it is tackled in the literature, this limited amount of search moves. But now I have to make a second criticism to differential evolution. And it is that although these search moves are limited, these structure can still be excessively explorative. And what happens basically, it happens that the D in some conditions, or let's say SPRO in many cases, might just wander around So keep on sampling points and not improve upon the performance. And this behavior is called stagnation. It's pretty common in evolutionary algorithms, or very common in swarm intelligence algorithms. And what I have to say is that differential evolution very rarely converges to some point, at least when the dimensionality is not very low. And the high diversity is often maintained, even in micropopulation, when I'm using a micropopulation. So, what I'm saying is that besides the limited amount of search moves, it seems that D is not very good at using the search moves. So, what people have been doing has been to vary the pool, so to restructure this pool in order to exploit in the best way or in a better way the pool of search moves. So, this is of course done in order to mitigate the stagnation effect. One way is basically to use a parallel differential evolution or structure the population. So it means that I can subdivide the population into islands, and I can run the differential evolution by selecting the individuals from different islands, and therefore I have less search moves in each island, and in this way I can exploit them and then exchange the information from one island to another. A very similar concept to the concept of a parallel D is at the end the concept of the DGL, of D with global and local mutation, where global and local in this case are in terms of indexes within the population. So we are not talking about indexes we are not talking about neighborhood in the space. We are talking about neighborhood within the population indexes, within the population list. And the mutation is therefore a contribution of, is generated by two contributions, one, let's say, global and one local. And in some senses, this is quite similar to a parallel, because it is making use of a restricted amount of points in this local contribution in order to enhance upon the performance. Or this is actually very simple. I'd like to spend a couple of words on this. It's, in my opinion, a very beautiful idea. And it is the population size reduction. It's super simple, so I can quickly explain you. Simply, you have a D. D is evolving. There is a schedule, and the population size is halved every now and then. So you have a schedule, and it is reduced progressively. And this exactly proves what I'm saying. That if we restrict the pool and we try to exploit the population, then we obtain some improvement. So that green line here shows the D with population size reduction. And so the algorithm at the beginning is trying to somehow to explore or to use all the possible search moves. So it tries to exploit everything. Then it gives up exploiting everything, and then it tries to exploit just a part of it, and then a smaller part and a smaller part. And at the end it becomes extremely exploitative, and it focuses just on some search moves. This, called proximity mutation, is another modern D variant that basically, it uses a probabilistic criterion, but in a nutshell, the idea is that the individuals that are used for recombination are individuals which are spatially close to each other. And this is somehow another way to enhance the exploitation. So the fact that this promotes a clustering of let's say, in the search, but you can think that I'm somehow structuring the search. I'm subdividing the pool of search moves, and I'm trying to exploit what I have in several parts before the budget exhaustion. This is another modern algorithm, and this is called MDPBX, and in this case, I have a component of the mutation that selects the individual with a high performance, but I would like to spend a couple of words on the crossover. And in this case, the individuals undergoing crossover are those that show a best performance. So also in this case, it's a pretty complex algorithm with many parts, but so I'm focusing on that. What is doing? What is this algorithm doing? It is essentially increasing the selection pressure, or it is exploiting, or it is adding some exploitation effect within the D framework. So now that I've, let's say, given you an idea of how the literature looks like, I would like to pose a question, and it is: so is the differential evolution an evolutionary algorithm? Well, it makes use of mutation, that is a perturbation. It makes use of a crossover, that is pretty typical in evolutionary algorithms. But unlike the evolutionary algorithms, the selection does not require any sorting. So if you are, for example, familiar with genetic algorithms, you know that, for example, you have this tournament selection, or you might have a roulette selection, and all of these mechanisms require a population sorting. This one does not require population sorting, but there is a one-to-one replacement. And this one-to-one replacement, where basically the offspring is killing the parent when it is outperforming it, is nothing else, or it can be seen like a position update, like a position update of a swarm intelligence algorithm. And so in this sense, I can say I cannot be that sure that the differential evolution is an evolutionary algorithm, or behaves like an evolutionary algorithm. In fact, the survivor selection, which is a very important feature of differential evolution in terms of behavior, makes somehow the difference in terms of diversity. This selection mechanism makes D different, or very different, in terms of diversity behavior with respect to evolutionary algorithms. Evolutionary algorithms are usually prone to a diversity loss, and this means that they are prone to premature convergence. As I was mentioning earlier, D is not that prone to lose diversity, so usually there is no diversity loss, and this happens already in moderate multivariate problems. Of course, if you try to implement a differential evolution in 2 variables, you are going to observe a diversity loss. But already in 30 variables, this does not happen anymore. And it's already stagnating in 30 dimensions. While if I try to apply an evolution strategy, I'm most likely, for the same problem of course, I'm most likely going to observe a diversity loss. Okay, then in a nutshell, I have been discussing about the search moves, I have been discussing about diversity loss, but now, okay, so what is the optimal diversity condition? So how does the E works nicely? Does it work nicely when all the population are focused somewhere? Does it work nicely when the population are all spread out? Does it work nicely when there's a kind of intermediate condition? This is a very, let's say it's a very interesting question, which does not have a full answer. And unfortunately, there is not really an ultimate answer because it appears to be very much problem dependent. But I have been observing myself that if one individual is a way better than the average of the population, so if this individual is called superfit, then the D works very efficiently. So in terms of diversity, this is a very interesting thing. So if I kind of drag one individual by applying a local search or by applying something else at the beginning, and then I continue the search by means of just of simple DE, I obtain a much better performance. And I don't know, I found this extremely interesting. Here I show you some results. So okay, this is so-called superfit DE against the classical DE. And here, of course, with the same budget, I have this blue line, which is with the superfit scheme, and the red line, which is without the superfit scheme. Here there is a magnified picture to show that the problem was not solved at the beginning. So, and you can see that you are having a way better behavior with a superfit differential evolution. So, in summary, D contains a few drawbacks. So, well, this is a kind of a sentence that appears in many papers. D is an efficient and versatile optimizer, which is almost like a commercial of differential evolution. But what are the drawbacks? At first, the pool of the search moves is somewhat limited. The D, nonetheless, can be, or in an apparent contradiction, can be excessively exploratory. And in already relatively high dimensions, like 30, or, well, moderate, it's not really high dimensions, but already in 30 dimensions, it stagnates. So, what to do? The first thing is to integrate additional search moves. And the second thing is to try to exploit the available search moves. And so, in order to quickly, before the budget exhaustion, obtain improvements. So, as final considerations, even though this is not the last slide, I have still a few minutes. Minor modifications of perturbation of the differential evolution scheme can lead to major improvement in the algorithmic performance. So, and this is a kind of important thing, and but not all modifications are the same. According to my view, it is definitely fundamental to be able to explain what each operator is doing, and to understand the why we are modifying the scheme in a way rather than another. And so, well, what I think is that, for example, is if we are able to see, well, it's not so difficult, how IDE moves and which kind of search logic there is in order to generate a new string, then I can try to use a different search operator which performs a different kind of movement. And I should understand that it should be different, and I should understand what it does in order to improve upon the D scheme. The designer should understand the entire algorithmic structure, and well, what I like to say is that the designer should build up every time the algorithm by a bottom-up logic. So should not consider like, well, I have a paradigm, then I make a perturbation of it, and then I've got a new algorithm, then I've got a new paper. But should take a different approach. So it should be like, I'm designing the algorithm because I want to solve a certain problem, or because I want to solve a certain class of problems, and I have to know exactly what operator is doing, what each operator is doing, and how they are interacting, how they are compensating each other, and so on. And a very important thing is to keep the algorithm as simple as possible. And this is what I like to call Occam's razor principle. And the idea is that if the algorithm, so well, what I was showing in that paper is that very simple algorithms can outperform extremely complex modern algorithms if the design is performed in a proper way, where in a proper way means somehow what I was telling before, that we know what each operator is doing. And we are sure that nothing useless is happening. And this, so in other words, means that a simple algorithm is easy to be implemented, can be implemented in limited hardware conditions, and most importantly, is easy to control. So, and if I can control the algorithm, I can know what the algorithm is doing. Therefore, in the long run, I can explain how to design the algorithm to a machine, and the machine can perform the design instead of me. This was the last slide. Thank you.
Thank you. It's a nice presentation. I enjoyed it. I have one question regarding the diversity.
Yes.
And we always say diversity is very important in evolutionary computation. That's true to some extent, but I think little differently. Diversity is required at the beginning until we reach the region of interest. Once we reach the region of interest, actually the rest of the region is irrelevant. So my point is, diversity is important, but how long we should consider the diversity? You understand what I mean? I mean, suppose you're optimizing in a large search space, and optimum in one side of the search space. I need the diversity to reach that result. Once I reach that result, not necessarily the optimal point, but that region, the rest of the search space is irrelevant to me. So diversity is required, yes, at the beginning, but later part, I can ignore the diversity or use the diversity for certain zone only, certain reason only.
Okay, what I meant in there is that, so I take your example, if you have a large search space and there is one optimal basin of attraction, and so at the beginning the diversity is high, then after a while one solution managed to jump within that basin of attraction. And so you're saying that I'm not really interested in all the other individuals.
Exactly.
But
not all the other reason. The individual in that region, yes, I am interested.
Yes, but I would like that also the other individuals move to that region in order to dig down the basin of attraction, because I do not have because I need that the vector, that donor vector becomes small. Otherwise, I'm keeping on sampling around, but I want to dig down. So I need at least another one. So basically, in a depopulation, according to my understanding, it's important that so each point has at least one close fellow, and then it can dig down in order to exploit. Otherwise, it doesn't exploit.
Yeah, but there is the restriction to reduce the population size. Otherwise, you are having excessive competition.
Yes. Okay. Yes, I see your point.
Yeah. Thank you.
Yes.
Any more questions, please?
There is one. Oh, one.
It's a very interesting talk. I'm just wondering, how do you ensure global optimality, especially like in situations where your population is shrinking?
Yes.
How does the algorithm come out of local optima?
Oh, well, the honest answer is simply you cannot guarantee any optimality in pretty much any of these computational intelligence optimization algorithms. So, and actually, what happens when you're shrinking the population is that you are doing some of the opposite. You are giving up the fact that you are finding the optimum, and you're trying to exploit what you have in order to reach the better that you can before that the budget is done. And this is, I mean, in some cases, in many engineering problems, the search of the optimum is an enemy of the search of the good. So actually, okay, this somehow would start let's say a broader conversation that I would shrink a bit and just say that dimensionality plays a great role. So when you are trying to solve a problem with a relatively low dimension, you're still attempting to find the global optimum. But in 1000 dimension, you simply can't. So what you have to do is to exploit as much as you can. And because I mean, normally, typically we have something like 5000 by n dimension as that's what usually is given as a standard, or in some cases 10,000 the amount of dimensionality. But while this is a linear formula, the increase of the complexity is not linear, and therefore 10,000 times n, a budget of 10,000 n in 10 dimensions is quite a big budget, maybe even enough to find the optimum. But in 1000 dimensions, it's absolutely not enough, and you can't. I don't know if this answers the question.
I'm working routinely in millions of dimensions.
Okay.
But my question really related to the three initial seeds. Your discussion of diversification of search moves was all after that choice, but has there been any work to actually be more intelligent about choosing the seeds or the directions that a pair of seeds?
You mean for the initial sampling?
Yes.
Yes, there is some work also in that direction. It's, well, if you can, somehow the superfit scheme that I was proposing at the end is something that at least partially answered to your question, because if at the beginning I choose one special point that has been improved by a different procedure, then I get overall that the algorithm is performing better. So I was not really, I mean, I cannot say like that if I use, for example, a distributed sampling of a lightning hypercube, I do not really see any major, at least at the general level, any kind of major improvement. So let's say at least a partial answer to this question is that if I get one that is much better than the other, so if I have one special point that is sampled in a special way, then I tend to get a better behavior of the algorithm.
But you're actually using two of the points to set a direction.
Yes.
But if the underlying space, I mean, you drew things with contours, but if you drew things with flows, there are flows.
Oh.
If you can choose flows that are more likely to take you from a poor solution to a better solution.
Okay. Well, actually, there is some work also in this sense. So basically, okay, now you are telling me that instead of picking up random points, okay, that's one. It's the very basic scheme. So you can say I can try to use some information about the gradient. Is this in order to be sure that yes, there is, for example, one scheme which I was not mentioning here that is called the trigonometric differential evolution, which is going to do pretty much this. So yes, there is some study in this regard, and at least in some cases, it is showing some good results. Okay.
Has there been any investigation? If you imagine you have two populations, one is moving forward slow in time, and one is moving forward fast in time, and they are in some way interacting.
Okay. Well, that's basically the case of the islands. But you're telling me two islands instead of. Is this what you mean? Because if you have multiple islands, you have different speeds that are because it depends on how the points are sampled. What do you mean by slowly? You mean speed?
Yeah, I thought about two separate systems, and one is having a more frequent, and one has a less frequent update, and they have a kind of interaction scheme.
I'm not aware of any study that is exactly of exactly this implementation. Are you referring to something specific or throwing an idea?
It's just an idea.
Okay, I will be happy to test it. Or do you want me to give to make a conjecture of how this would work?
Yeah, I would be interested if you would expect that this is performing better or worse or has no influence.
I would expect that I might get some improvements if I can have some migration from one to another. So if, for example, the one that is going slowly is donating some individual to the other, then that's going to be beneficial for the global algorithm. I have done actually something that more or less is like this, in the sense that I had not only two, but I had multiple islands, and they were of two kinds. One was working with the population shrinking, and the other one was working with fixed population. Population shrinking is more or less a boost, basically. It's a boost to the convergence. And then at some point, it was migrating from this population with the shrinking to the others. And that was giving some reasonably good results, but I was not that much satisfied. I mean, it's not extremely straightforward to implement this.
So if there is no more comments or questions, you have.